jump right into chapter 5, and we're going to start with scatter plots. So, what is a scatter plot? Well, it's a graph of a bunch of points taken from probably data collected. So in this case, we have people's test scores and how they relate to the number of hours that student studied. So let's plot all these points. So there is 1, 50. So that's 1 hour studied, getting a score of 50. 1.5, so an hour and a half, so 1.5, 55 is about right there. Okay, and if you want to pause the video to finish graphing these points, I would encourage you to do that now. But I'm going to finish graphing these in 3, 2, all 1. All right, so 2, 52, that point would be about right there or so. 2.5, 68, about right there. 3, 71. And you don't need to be like super crazy exact. 3.5, 68. 4, 85, I believe is right there. 4.5, 88. Let's just say there. 5, 95. 5.5, 93. Right there or so. And 6, 100. Okay? So this is like a scatter plot. Just plotting a bunch of points taken from data, from something kind of like real life. Now, something I would definitely want to say and make it a point to say that, I mean, real life can be not exactly like an exact science. Like, you see how these dots are definitely forming kind of like this uphill, linear type looking thing. Like they're almost making a line, but they're certainly not making a perfect line. Like every single one of these dots are not going to be on like the same exact line, but they're pretty much making a line, So yeah, like real life is never like exact. There's all kinds of different like imperfections, even in like real life patterns and real life mathematics. You know what I mean? But for the most part, it looks like the number of hours someone studies and the test scores, it seems like there's a pretty solid relationship in that the more hours you study, the higher the test score is going to be. Now, does everybody follow this pattern? No. Again, real life is messy. There could very well be someone that studied for half an hour and got a perfect score. So could there be a dot right there? Sure. There could be a student that does that. Could there be a student that studied for 5 hours and got a 55 on the test? Yeah. So there could be a student that their dot would be right there. You know what I mean? But if you graphed think about it, especially if you graphed like 1,000 students, right? There's going to be dots all over the place, probably, right? But wouldn't there be probably for the most part some type of trend pattern that follows through for the most part? I would think probably. Oh man, look what I did. Let's undo that. Yeah, that's. Whew, that was a close one. So yeah, anyway, so this is a scatter plot, and hopefully the scatter plot shows some type of pattern. And this actually shows what's called a positive correlation. So this is a positive correlation. That's kind of like a vocabulary term. The more hours you study, the what your test grade? The higher your test grade. That's what a positive correlation means. It doesn't so much just mean that we're going uphill, but that is true also. So if you see dots that are making kind of an uphill line, that's a positive correlation. But what it really means is that as one variable increases, the other variable also increases. And also vice versa, people. As one variable decreases, the other variable also decreases with it. So the two variables go up together and they go down together, and that's how they kind of affect each other. So yeah, here again, here's kind of like the positive correlation. It's kind of going uphill. And another example of that would be number of overall minutes played versus what? Like, let's say this was like LeBron James in the NBA. Okay? The more minutes he plays, right? Like, let's say as they increase. So as the number of minutes played increases, what else might also increase along with the minutes played? I would think number of total points scored. So these two variables have a positive correlation because, you know, they would increase together, but they would also decrease together. So like the less minutes LeBron plays, the less points he scores. And the higher minutes he plays, then the higher points scored. And so, of course, a negative correlation would be kind of like downhill. But that really means that when one variable increases, the other variable is actually decreasing. So one increases, the other decreases, and vice versa. And let's see an example of this. Yearly salary versus amount of debt. Yeah, maybe. That's probably not the bestest example ever, you know, because this is definitely not going to be a perfect sort of situation. But I think if you survey enough of the population, right, I would think like the more someone's yearly salary is, probably the less debt they have. I don't know. It's not like a cut and dry thing, but, you know, just for the sake of argument, let's go with this one, that the higher salary you have, the less debt you probably have, and maybe like the lower your salary is, the higher amount of debt you could have, you know. Now that doesn't have to be true, but let's just kind of assume that's true for like at least a large percentage of the population. And no correlation, what would that scatter plot look like? If two variables had like no relationship whatsoever, no correlation whatever with each other, then you're just going to kind of see like a bunch of random points, you know, somewhere. And so temperature and toothpaste sales. Temperature and toothpaste sales. I don't think those would have any correlation with each other, you know what I mean? Like, I don't think like the higher temperature is, like I don't think the hotter it is outside, you know, the more toothpaste sales are going to be, or whatever the case might be. Actually, now that I'm actually thinking about it, I don't know if for this particular example the dots would look like that. I bet the dots would look kind of like this. You know? Like, let's say this was temperature, right? Like 50 degrees, 60 degrees, 70 degrees, 80 degrees. I would think toothpaste sales are probably pretty consistent, like whatever this number might be, like 5 million tubes of toothpaste sold that day. So I would think like on a 50-degree day or something, I don't know, about 5 million. I'm kind of like just kind of freestyling this right now, but let's say on a 50-degree day, 5,000 tubes of toothpaste sold. Well, on a 70-degree day, there might also have been 5,000 tubes of toothpaste sold. On an 80-degree day, about 5,000 tubes of toothpaste sold. On a 60-degree day, 4,800 tubes of toothpaste sold. On a 55-degree day, 55,000 or 5,500, 5,500, whatever, right? So I think this might be a pretty good scatter plot for, toothpaste sales compared to the temperature outside, which this isn't really going uphill, it's not going downhill. So you might also have to call this a no correlation type situation. So real quick, what do you think here? Based on the titles, what kind of scatter plot would we probably see? Positive, negative, or no correlation? Amount of rainfall versus number of people attending a game outside. What do you think? As rainfall goes up, does the number of people attending go down, go up, or doesn't really matter? I would think negative. Okay? I mean, I would think across the board, right? Let's say in professional baseball. I would think for the most part, the more rainfall there is, the less people would attend. Now I know there's probably some anomalies out there, some outliers where, let's say it was the World Series, and it could be pouring, but the place would still be packed with people. I get it, but I would think, over the course of a lot of data, like all the games, I would just have to assume that as rainfall increased, the attendance decreased, and that's what a negative correlation is. How about number 2? The amount of ice cream sold versus the temperature outside. So do you think as temperature rises, the amount of ice cream sold would also rise? Or would it fall? Or do you think there's no connection there? I think for the most part, you'd probably say there was a positive correlation. I know there'd be some anomalies, right? I mean, I don't know. But I would think for the most part, that as temperature rose, that more people would be buying ice cream. So positive correlation. And as temperature dropped, the amount of ice cream sold would probably also drop. Right? Number 3, amount of hot chocolate sold versus temperature outside. So the hotter it gets outside, I would think the amount of hot chocolate sold would go down. Like especially at a sporting event, right? Sold, go down. So that would be a negative correlation, wouldn't it? That would be a negative correlation. Because as one goes up, the other goes down, and as the other one goes down, the other one goes up, right? Negative correlation. And that's actually, ignore that, that's actually the first part done. That's like the easier portion of scatter plots, just kind of what they are, the correlations, but the other major thing with scatter plots, definitely thinking of the keystones. The people that write the keystones love asking questions about scatter plots. More specifically, the lines of best fit. So this line of best fit, the keystones love asking about the equation and they love asking about predictions based on that line of best fit. Okay, so really, first of all, let me just kind of say that the line of best fit, really only makes sense when like the all the points are pretty much forming like a linear type relationship, and it's going downhill or uphill or whatever. And if you were going to like draw a line through the heart of the dots, like if you were going to think, if all these dots could be summed up in one line, what would that line be? And that would be like the line of best fit. And it's actually sort of best if a computer program like does it for you, but really it's when you have to do it, it's kind of about like just eyeballing where all those dots are, kind of going with like your gut instinct, like what do you think the heart of the dots are, like down the middle. The only rule of thumb I can really even say, because I really don't think it applies all the time, so it's not really so much a rule, it's really like just a kind of a vague guideline. But you could use it and say like the same number of dots have to be on both sides of the line, but I'm not even sure that's really true. Again, just sort of a guideline, not really a concrete rule. But I would like to think that, especially on tests like the Keystones, the line of best fit would already be there, and if the line of best fit is already there, great. If the line of best fit is not already there, then there's going to be a little bit of leeway, because drawing the line of best fit is not going to be an exact science unless a computer program is doing it for you. So here we go, coming up with the equation of this line. All right, now here's what I'm going to recommend we do. The first thing you're going to want to do is pick 2 points on your line, on the line. See, like, hey, this point and 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 this point. None of these points matter, except maybe this guy. But the points you pick have to be on your line. And this is something you might want to write down, okay, in the margin or whatever, make a little note. The farther apart you pick your points, the better. So I'm actually going to pick this point right here, and I'm actually going to go with this point right here. And that's 4 comma, I think, 4 comma, yep, 21, 22, 23. So 4 comma 23, and here is 12 comma 3. Okay? 12 comma 3. So those are my 2 points, right? Because if I had to come up with the equation of the line, we've already learned that it's pretty simple to figure out the equation of the line as long as I have 2 sets of coordinates for 2 points on the line. Okay? I mean, bottom line, well, I'll just stick with one strategy here. As long as you have the slope of the line and 1 point, you can plug into that formula to make the equation of the line. All right? Now, we don't have the slope, but knowing 2 points, we can figure that out. So I'm going to do 23 minus 3, because that's y sub 2 minus y sub 1 I'm going with. And then I'm also going to, now that makes x sub 2, 4 minus 12. And so that's going to give me 20 over negative 8, which reduces to 5 over negative 2, or just negative 5 halves, right? Now, if you want to write that as negative 2.5, I guess I wouldn't blame you too much. That wouldn't be insane, obviously, but I'm going to go with like negative 5 halves here. Now, on a side note, it's not like we don't have the line in front of us. You might be thinking to yourself, self, why don't I just count my rise and my run? Okay? And hey, go for it. There's nothing too wrong with that, except there might be something that trips you up in that I know here every single box is counting by 1. I mean, look, 4, 5, 6, 7, 8, 9, 10, 11, 12. And down here it's 1, 2, 3, 4, 5. But look, gang, I'll point you to this right here on the next problem. And I'm going to go ahead and even reveal that I think I'm going to go with this point. And again, the farther apart, the better. So I'm going to go with that. So look, when you count, check this out. You might forget, or you might just naturally be tricked and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 as my rise. Again, like 1, 2, oh, but guess what? The rise here is not 15 because it looks like here we're making jumps of 2. See, look, 20 to 30, that'd be 2, 4, 6, 8, 10, yeah. So this would be by jumps of 2. So you have to notice how the y-axis, how the x-axis is being scaled and labeled and broken up, because every box here would be like 2. So it would really be, if you were counting, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. The rise is really 30. So if you want to count your rise and your run, be my guest, but just make sure you're counting correctly. And I also want to say, as sort of to summarize that, the formula is never fooled. All right? Plugging in the actual coordinates is probably how you want to go. The formula is never tricked by how the x-axis or y-axis is labeled. All right? And so now I'm going to do what I've done like with you in the previous chapter, and I'm going to pick, what was I calling y1? Looks like I was calling this one my y1, right? So I'm going to plug in 3 for my y1. I'm going to plug in -5/2 for my m that I had to find off on the side. And then I'm going to plug in 12 for my x1, right? Remember, this is called point-slope form, and the ingredients are going to be a point, 12,3, and the slope, which I had to find off on the side. And just like, just kind of like the routine here is to distribute. Let's see here, that's going to be a plus. -5/2 times -12 makes +30. And then I'm going to add 3 to both sides to finish my equation of -5/2 x plus 33. Okay? Now, before we do the prediction, let me just kind of follow up a little bit and summarize a couple things like this. So when you are shown a scatter plot, and you also might even be shown the line of best fit for free, and if you are asked to find the equation of the line, sometimes it's going to be doable to just look at your line and get the m by counting your rise and your run. Just please do it carefully. Again, you probably just want to go with this. And you might actually be able to eyeball your y-intercept. So if that's the case, people, if that's the case, maybe I can even show you an example. Maybe like on this next one. Maybe on this next example, we're going to be able to just kind of go like, wait, this line, it looks like this line is going to be crossing the y-axis, and the y-intercept is just going to be, what is this, 12? Because it's going to go 10, 12, 14, 16, 18, 20. So, whatever, I mean, I don't know. We're estimating, that's fine to just kind of estimate. So if you can just guesstimate it there, hey, whatever, that's fine. Now here, it looks like my y-intercept ended up being 33. Could we have just eyeballed that by keeping this line going and seeing where it was going to intersect the y-axis? Maybe. So again, sometimes you can just look at the line and it's crystal clear what your m is, and it's crystal clear, or clear enough, what your b value is going to be. And then, hey, if that's the case, be my guest, just plug into y equals mx plus b. But I'm telling you, as a more general, consistent strategy for these things, just trust me for right now, it's probably going to be best as a consistent one strategy and one strategy only to just pick two nice points on your line. The further apart the better, okay? The further apart the better. And calculate the slope using your formula, and then plug in to point slope form like I did here, using one of your points and the slope you just got done finding. All right? Now, finally moving on. This is a long lesson, sorry. There's a lot to cover, as simple as this concept kind of is, like these directions of giving the equation and predicting. But hey, so stay with me here, people. So moving on to the predicting. Predict how long it would take for a group of 10 people to escape the room. Well, look, check it out. Sometimes this type of question is as easy as looking at your graph. Okay, 10 people. And this is always going to be based on your line of best fit. So I know there's actually already a point there for 10 people. So there was a group of 10 that was surveyed, and it looks like they said about 12 minutes or something, or almost 12 minutes, or 12 minutes, whatever this dot says right here, right? But hey, if we were going to predict, another group of 10 people, we would go with the line of best fit as a predictor. And so look, sometimes these prediction questions are just based on the line, because you can just look at it and go, so for 10 people on my line, it looks like it would be, 8 minutes would be my guess, my prediction. 5, 6, 7, 8, yeah. So sometimes the prediction question is that easy, that you can just kind of like eyeball your line of best fit for 10 minutes, take that back, 10 people in the group and go, well, it looks like 8 minutes. And that's how easy it can be sometimes, but we're going to see in a minute that it's not always that easy, and I'll show you what to do when we get to that, when we cross that bridge. So here we go. What's going to be the equation of this line? And I'll change things up a little bit, right? Why the heck not? Let's just plug into y equals mx plus b. I bet I can figure out m pretty good, and again, it looks like my b value is going to be pretty much 12. And if it's supposed to be 11.9 or 11.5 or 11 or 12.2, then whatever. I mean, look, see, if you know for a fact that this point is on your line of best fit, and this point is on your line of best fit for sure, that'd be a different story. Then I can be held to a little bit of a higher standard with coming up with like an exact b value, an exact slope. But look, if I'm just guesstimating that this point's on my line and that this point's on my line, then I can sure as heck just guesstimate my slope and guesstimate my y-intercept, and it's probably not going to be that big of a deal. So here we go. Remembering that this goes by twos. It's not 1, 2, 3, 4, 5. It's actually 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So my rise is 30. And then my run, let's see, are we going by ones down here? Yes, we are. So when I count my run, I can just count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it looks like my slope is going to be 30 over 11. What's that decimal? Like 2.9-ish or something? Whatever. I guess you don't be surprised if you see the slope as a decimal sometimes, even though it really should be a fraction. And I already know my b value, so check it out. What the heck am I doing? I'm getting ahead of myself. So yeah, I mean, there's a pretty good equation, but you know, again, it might be in your best interest to go with the strategy from before of taking these two coordinates of 3, 20 and 14, 50 and finding slope with the slope formula and then plugging into point slope form to get our equation. And you know, the next example will really prove like why you should probably do that all the time. But again, sometimes it really can be as easy as, count my rise and my run for my slope, even though you got to do it carefully. Count that off for my m, eyeball my graph where it's going to cross the y-axis for my b value, and there's my equation. All right, now the prediction question. Predict what it's going to be for 36 games. Okay, well, 5 games, 10 games, 20 games. Ooh, man, 36 games. That's way out of bounds. I don't think I'm going to be able to just kind of, go up to where my line is, and because that's like way out of bounds. So here's what you do. You have the equation now, right? Y is the number of strikeouts. X is the number of games pitched. So 36 games, I can go ahead and just throw that in, plug it in for X. So to make your prediction questions, to answer those prediction questions, feel free, if you have the equation, just to plug it in, man, okay? So I'm going to do that now. 30 over 11 on my calculator times 36 plus 12, and I'm getting like about 110.18 strikeouts. So, I'm going to go with that as an answer. About 110 strikeouts would be like my prediction if someone pitched 36 games. Okay? So let's do this example. Let's see if there's any reason to do this one. Maybe I'm going to... But here we go. Now, thinking about what my M is and what my B is, listen very, very carefully. As tricky of a curveball is that, like, these boxes are not jumping by one, because people get tripped up by that again, right? Like, that's a curveball that you got to be ready for. that when you count your rise and your run, it's not always counting by ones. You know, here's an even trickier curveball that people might fall for. You might look at this and go, well, I can handle the slope. I'll count by tens when I go up, and I'll count by 2.5. Yeah, whatever. Even if you can handle that, you go, and I can tell where my line is going to cross my y-axis. I can tell that my b value is going to be like right here. 50, 40, 30, 20, whatever. It looks like my b value is going to be about 15, right? Right? Don't write that down. Right? Wrong. Wrong, 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 wrong. Because guess what? Sorry. Come on. This right here, which seems like the y-axis, is not really the y-axis. People, the y-axis is not really here. Look at this little jagged mamma jamma right there. That means that we have skipped so many x values, and that, see this 40? It was supposed to go 50, 45, 40, 35, 30, 25, 20, 15, right? The true y-axis is not even here. It's way over to the left. Like this. Okay? Like you're trying to tell me that it crosses the y-axis. The real y-axis is way over here. So that is, people, another reason why I don't know if you just want to always eyeball the graph, especially for your b value, because situations like this. So again, it's not just the counting the rise and the run can be tricky, and therefore you should really just use the M formula, right? It's also that it's not always possible for you to eyeball where your line is going to cross the y-axis. It's not always like even possible for you to really eyeball what your b value is going to be. So again, this is what I think we need to do. We need to figure out two nice enough points on your line. The further apart, the better. And so here, it's going to be, oh my gosh, 40, 45, oh man, this is 47.5. 40, 45, 50. So 47.5 is right here, people, comma, 60. And this point that I picked up here is 90 or 85? It's 85. So 85, comma, 160, 170, 180. And so once I have those 2 points, I'm going to let the formulas just do the work. So I'm going to do 180 minus 60. Okay? Yeah. 180 minus 60. Is that right? And I'm going to do 85 minus 47.5. So 180 minus 60 should be 120. 85 minus 47.5 is 37.5. And just to mix things up a little bit, let's actually just go with a decimal for my final slope. Let's get nuts. 120 divided by 37.5 is 3.2 exactly. All right, that works for me. And so here we go. The next thing I think you should make part of your official routine is plugging into this formula. And so let's see, we were using this one for our x1, y1. And so my y1 is 60. My slope is 3.2. And my x sub 1 is 47.5. And so solving for y and everything, when I distribute my 3.2 there, and then 3.2 times negative 47.5 gets me, let me just double check that, 3.2 times negative 47.5 is negative 152. And then when I add 60 to both sides to get y alone, let's see, I get negative 92. So there's my final equation. And it's not like that is like the one and only correct equation, because depending on what points you picked, the equation could be a little slightly different. But all right, now the prediction question. 25 degrees. Once again, I don't know if I could just eyeball my graph where that falls on my line of best fit. So again, you might just want to make this part of the official routine. Figure this out by plugging 25 in for x. And then crunching those numbers. So 3.2 times 25 and then minus 92, I'm getting negative 12. So on a 25-degree day, we could expect and predict negative 12 customers, which admittedly doesn't actually make any sense. So once again, real-life math, not always perfect, not always an exact science. So, this equation doesn't really make sense, all the time. Certainly doesn't make any sense when the temperatures get as low as 25 degrees. It's not possible to have negative 12 customers, but that's the answer based on the scatter plot, based on the line of best fit, which produced this equation. Okay? And let's see if that makes sense. So what was 25 degrees? So yeah, right here, which that does sort of fit my answer of negative 12 customers, right? Negative 12 customers. Oh yeah. Let's see if I want to include the fourth and final example in the video. Is it worth it? Let's see. So, maybe not so much, right? I mean, we do have a jagged line here and everything, but you could actually do here, as much as I think your official plan should be to use this formula, maybe choosing this point and, I don't know, this point, whatever, followed by this formula, followed by plugging in 30. Well, definitely, because you can't really see 30 on here. So you would then plug in 30 to your equation. This right here, is this actually where the y-axis is? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So guess what? This is the y-axis. This truly is the y-intercept. And so your b value is basically going to be 136, 137, about 138. So if you just want to figure out your m and just use 138 for your b value, that would be doable here. and then you could have your equation and plug in 30. But I'll leave that to you. And if you need to ask any questions in class, obviously that is encouraged. So hope probably one of the longest videos in this class ever, but totally, I think, worth every second. So that is section 5.0 on scatter plots and lines of best fit.